Okay, let's go through this sample final. I added another column here because after I changed this from the original sample final said just find the trapezoidal rule Riemann sum for this, and we could do it with what I had, but now I want you to do a Simpson rule. And to do a Simpson rule, we need to do either M3 or T3 or T4 or M4. Well, midpoint's kind of the one that's restrictive. And so if we're going to have a midpoint, we have to have an interval like that. So that's in the middle. So from 0 to 4, use the height at 2. From 4 to 8, use the height at 6. And so I need another one here to be able to do midpoint 3. So we'd be doing a Simpson 6, which is a midpoint 3, which is twice as good as a trapezoid. So we multiply it by twice, weight it, plus a trapezoid 3 divided by 3. Because there's 2 here and 1 here, and we have to divide by 3. Okay, so we need to calculate the midpoint 3, and that will be at the midpoint it's 2.3, and the width of the interval is 4, but all these are 4, and so I'm going to take 4 times all of them at once. So at 2, the midpoint here between 4 and 8 is at 6, and the height is 1.7. And the midpoint between 8 and 12 is at 10, and the height is 0.3. So we have this plus this, that's 2, plus 2.3 is 4.3 that we have to multiply by 4. And so we're getting the midpoint approximation of the area under this graph is 17.2. All right, now let's figure out the trapezoidal 3. So that's going to be, we're going to do 3 intervals again. So the interval width is 4. 0 to 4 is 4, 4 to 8 is 4, 8 to 12 is 4. And we're going to do not the midpoint, but the average of the left and right. So 2.1 plus 2.5, which is 4.6 divided by 3. Well, that one turns out to be 2.3. That happens to be right in between. I don't think that's always going to happen. Plus the average of the height of 2.1 and 0.9. That's 3 cut in half is 3 cut in half, which is half. This one was 2.3. This one is 1.5, not 1.7. So it's a little off from the midpoint estimation. Plus between 8 and 12, that's 0.9 and 0.1, which is 1.0 divided by 2. So we have 2.3 plus 1.5 plus 0.5. So that's 2 plus 2.3 is 4.3 times 4. And this one's going to work out to be exactly the same as that one, which is surprising, but anyway. So if we take 2 of the midpoint, which is follow the Simpson rule, it's going to be 17.2 times 2 plus the trapezoid, 17.2, divided by 3. Well, this is going to be 17.2. But I want to show the math on how I got it. Now I just want to check and make sure I didn't make any mistakes here. 2.3, 1.7, and 0.3. 2 plus 2.3 is 4.3, 16, and 1.2. Yes. Here we have halfway between 2.1 and 2.6, 2.5 and 2.1 is 2.3. Halfway between 0.9 and 2.1 would be 1.5. That's right. And halfway between 0.9 and 0.1 is 0.5. And that's 2 plus 2.3 is 4.3. Yep. So these do come out to be the same on this one here. Okay. All right. Find the average value of the function, this sine function between 0 and pi over 2. Now the sine curve, of course, looks like this, and the 2 makes it half as long, so it normally hits at pi, so this be at pi over 2. And so we're supposed to find the average value. So it goes up and it comes down. The average value would be something less than 1. And to find average value, you find the area under the curve, which is the integral from 0 to pi over 2 of, wait a minute, sine of 2 times pi over 2 is pi. Sine of pi, yeah, is 0. That's correct. It's going to be the integral of sine of 2x dx. This will give me the area under the curve. And then to find the average value, I divide by the width of the interval, which is pi over 2. Or if you want, pi over 2 minus 0. The book puts it out here as b minus a, 1 over b minus a. Well, I can just put it underneath. But anyway, I got to figure that out. The antiderivative of sine of 2x is, let's see, antiderivative of sine is negative cosine 2x, and the change rule would put a 2 underneath. So the derivative of cosine is negative sine, and so that negative makes it plus, and the derivative of the inside is a 2, which cancels there. So this is the antiderivative of this. I have to evaluate it from 0 to pi over 2 over pi over 2 minus 0. Now, I could just type that in the calculator, but I'm doing it here. Pi over 2 times 2 is just pi. Cosine of pi is minus 1. So I get minus a minus 1, which is 1 over 2 minus, put it in 0. Cosine 0 is 1, so it's minus 1/2. So that turns out to be 1. And this is all over pi over 2. So divided by pi over 2 is 2 divided by pi. Now let's just do a little calculator checking on this. So clear, we want to do math 9, the integral of sine of 2x, close parenthesis. Let's see, make sure my mode is in radians. Yes. Nope. Close parenthesis. Variable is x, from 0 to pi over 2. This is how you type it in on the older calculators. You have to say what you're integrating, what the variable is, and from what to what, the limits. The newer calculators put it in the fancy print that makes it look like an integral. But anyway, that's that, which is the 1 that I said we had. We have to divide that by parenthesis pi divided by 2. And so we get an average value of 0.6366, somewhere less than 1. So decimal value of the approximate answer for this is 0.6367. But the exact answer is 2 over pi. Okay, we have an even function. Even means whatever it does on the right side, it does on the left side. And from 0 to 2, the area is 3, a positive 3. Since it's even, it would be a positive 3 on this side. And then from negative 2 to 5 for 5 about here, the total is 7. We got 3 plus 3, so there's just 1 more over here to make a total of 7, which means over here that here to here has to be minus 1, or plus 1, same as what's on this side. So from 2 to 5, there's 1. From minus 2 to 2, there's 6. And from minus 5 to 5, which is in the right order, there's 4, and 4 is 8. Now, if this had said odd, let's just do this one just in case it was odd. So if this was 3 on this 0 to 2, then it would have been minus 3 here. And if it's minus 2 to 5 is 7, well, this plus this is 0, so the rest of the way out to 5 would have to create an area of 7, which means back here would be minus 7. So if it had said odd, then 2 to 5 would be 7. That would be the answer. If it was negative 2 to 2, that would be 0, because those would cancel. And from negative 5 to 5 would also be 0. Next one. Find the indefinite integral for this. So there's no limits. You can't type this in the calculator. So the antiderivative of x to the 4th is x to the 5th over 5. This is x to the minus 2. Antiderivative of that is x to the minus 1 divided by the new exponent plus c. Or if you want to rewrite it, x to the 5th over 5 minus 1 over x, because that minus power puts it down there, plus c. Now it's tempting to say ln, but no, that's it. We've already done the integration. If I had to integrate that, it would be ln x. All right. Next problem. Use the fundamental theorem of calculus to evaluate. So you need to show me, I don't want you to just type it into calculator. I want you to use the fundamental theorem of calculus, which is find the antiderivative of this and then plug these in. And so I'll probably change this so that you have to do the fundamental theorem by saying to find the exact value. So this is 3 times 1 over x, so that antiderivative is ln absolute value of x with a 3. Antiderivative of x squared is x to the third over 3. Antiderivative of minus 2 is minus 2x. Evaluated from 1 to 3. And so if we put 3 in here, we get 3 ln 3. Absolute value 3 is 3, so I don't need the absolute value there. 3 in here is plus 27 divided by 3, or 9, minus 6, minus, now we got to put the lower limit, because we're going from here to here, so we take the end minus the beginning. That's what the fundamental theorem of calculus says. So if we put in 1, we get 3 ln 1, and that's positive, so I don't need the absolute value, but I put it, plus 1/3 minus 2. Now, ln of 1 is 0, so 0 times 3, that's 0. So I get 3 ln 3. Don't need the absolute value on it, but okay. And then we got 9 minus 6, which is 3 minus, let's see, plus 2, which is 5, and minus 1/3, so plus 4, let's see, no, yeah, 3 plus 2 is 5, minus 1/3, 4 and 2/3, if you wanted to reduce it some, but that would be exact value. A decimal approximation doesn't work. Here would have been okay. This is an exact value. I would hope you guys could do the simplification, but not necessary. Now we got to integrate this. It's not a definite, so you need to actually know the antiderivative of secant squared, and that is tangent x. And you need to know that this is x to the 5/2. So if you integrate that add 1 to that, which means 7/2. So minus x to the 7/2 divided by 7/2 plus c. And you could turn this over and make it 2x to the 7/2 divided by 7 if you want. And 7/2 is x cubed, square root of x if you want. Okay, let's look at 7. So this is feet per minute, and this is minutes, I think it said. Yeah, minutes. Okay. So the area under the dashed graph tells you how far that runner went. The area under the dotted graph tells you how far that runner went. So the area between must tell you the difference in their position. So I want you to graph the distance between them. I didn't leave a spot here for a graph, so you'd have to make it. If this was the test, I would hope I would do this for you. It's not always a guarantee. So the area between is representing how far dash is getting ahead. Now it says they start at the same place. So if we're graphing the distance between them, there's no distance between them to start. None. Now, if we look up here, this is 2 units over, and it's 2 units up, 2 feet per minute times 2 minutes. This represents a difference of 4 feet. It's not a lot of feet in a minute. So whatever's racing is really going slow. 4 feet per minute, 2 feet in a minute. Might be snails or slugs, something going really slow. Anyway, so we have the difference in the distance. So this is almost, there's a little less here, but a little bit more here. So this is about 4. And this one's missing some, so we could call it 3. So we could estimate this to be about 7. So I'm going to go 4, 8, 12, 16. So after the first 2 minutes, the dash is ahead by 7. And it's gaining on them. It starts at the same place, so there's no difference in their position. And it's up by 7 after 2 minutes. In the next 2 minutes, let's see. If I kind of just even this off about there and even this off about there, that looks like about a square and a quarter, maybe 5 here, maybe 6. So it's going to go from 7 plus 5 is 12 or 12 and a half or 13. A little bit more distance between them. And then this probably evens out to be about a square. I could estimate that to be about 4. If I'm at 12 or 13, I would get up to 16, 17 maybe between them. And then there's a little bit more that's going to give them a little bit more distance between them. Let's check and see how I'm doing here. This is a triangle. It's 4 to 8. So the base, you could call this side 4. And the height looks like it's about 9. 9 times 4 is 36. Divided by 2, 18. I should be up at about 18. 16, 18. Am I close? Yeah. All right. So now they're both going the same pace. So if the dotted stayed there, they'd just stay the same distance apart. They are not together here. Their speeds are the same, but the dash is ahead because they started at the same place and dash was going faster, slowing down but was going faster, and so got ahead by this area, that amount, about 18 feet ahead. So now we're going to find out what happens after that. Well, the dash stays going the same speed, but the dot starts gaining on them. He's behind, dot's behind because of going slower at the beginning. And we'll get caught up with them when the area in here is equal to the area here. This was 18. So we can do some estimating here. There's a little bit here and a little bit there. We could average that out. It looks like about 3 by 1, so maybe about 3 by the time we get to here. From 18 would be about 15. And then this looks like about, 2 would be like this, so it's a little over 2, so 15 to 13. And this looks like not 4 would be the whole thing, so 3.5. The dot's going faster, so this graph has to go down because if this was positive area, this becomes negative area as far as the dash is concerned. Dash is losing ground to there. And so it's down some more. And let's see. I did this one, so now I'm here. That's a little over 4. So that would take us, this is 4 units, so it's down a little over 4. And then this is 4, 5, a little over 5. So is this, let's see what the area is here to see who's ahead by 20. So this is 2, 3. This is 2, 4, 6, 8, 10, 11. Triangle 3 by 11, 33 and a half is 33 cut in half is 16 and a half. This was 18. This is 16 and a half. So dot hasn't quite caught up with dash yet. Will later, but not. So Steady Snail, who, if Harry the Slug is the dotted line, Harry the Slug is catching up, but Steady Snail, the dash is Harry. The dash, he started off ahead, and now he's losing to the Steady Snail, but the Slug is still ahead by a slight bit. I think we figured out 18 and 16 and a half by a foot and a half. Okay, that's the difference in the areas. So that's how much the difference in their position is. The area between the graph. Okay. 14. Nope. 8. Substitution. Well, I'm going to let u equal 1 plus minus 5x squared. Du would equal negative 10x dx. Divide by negative 10 dx equals du over negative 10x. So this is what goes in place of the dx. I have an x in the numerator, so this is the integral with an x. I have the square root of u, and I have, for the dx, I have du over negative 10x. The x's cancel, and square root of u is u to the 1/2. That's in the denominator. To move it up, it'd be to the minus 1/2 over negative 10. I can pull the negative 10 out, and I get negative 1/10. The antiderivative of u to the minus 1/2 is u to the plus 1/2, adding 1, divided by 1/2, plus c, but I need to change it back to x's, so it is c minus 1/2 times 10 is 5, and u is to the half. That's the square root of whatever u was, and u was 1 minus 5x squared plus c. Integration by parts. So x would get simpler if I took the derivative of it. So in my table, I'm going to let u be the x and e to the 2x dx be my v prime. E to the 2x dx, antiderivative of this is 1/2 e to the 2x. Derivative of x is 1 dx. And the by parts, this becomes uv minus the integral of uv prime. No, that's what we had, uv prime. So we have to do these. 1/2 e to the 2x times 1 dx. And the integral of e to the 2x is 1/2 e to the 2x. So this is another 1/2. So it's 1/2 x e to the 2x minus 1/4 e to the 2x plus c. Partial fractions. 1x squared minus 1 factors to x plus 1 and x minus 1. And that's a linear factor, so all I need is an a, all I need is a b. And now I got to figure out the a and b so that if I added these two fractions by getting a common denominator, it comes out to be a 3. So this one I'd have to multiply by x minus 1 and x minus 1. This one I'd have to multiply by x plus 1 and x plus 1. So a times x minus 1 plus b times x plus 1 needs to equal 3, identically equal. So we have ax's and bx's and no x's. So a plus b has to be 0. If I look at just the x's, a of them and b of them has to be 0 of them. And if I look at the constant, 3 has to equal negative a plus b. Now I could solve for one of these and substitute in the other one, but it says a is equal to the opposite of b, so negative a would be equal to b. So b plus b is 3. Another way to do this is I could b plus b, 2b equals 3, b equals 3 halves. Another way to do this, since these are opposite, I could just add them and I get 2b equals 3. So b equals 3 halves. So a must be equal to negative 3 halves, so that a plus b equals 0. So this problem turns into the integral of a negative 3 halves integral of 1 over x plus 1 dx plus cb was 3 halves, a constant, it pulls out because it's times 1 over x minus 1 dx. And if you do u sub for this, you'll get 1 over u du, which is ln of u, or x plus 1, times negative 3 halves. And similar with this one, this becomes ln 1 x minus 1 times a 3 halves plus c. Show the proper steps on doing this. 0 is not a problem in this, but infinity is. So we have to write the limit as b or a or something goes to infinity to make this a definite integral with not a problem on the end, 0 to b of e to the negative x dx. Now, this is a fairly simple one to integrate. If you don't know how to do it with a minus, let u be e minus x, and you can do the u sub and get it. But the integral of e to the negative x is negative e to the negative x, evaluated from 0 to b. We don't want to do anything with the limit yet. We want to put these limits of integration in here and get that difference, and then figure out what the limit does. So this is the limit as b approaches infinity. Putting the b in here, that's minus e to the minus b minus a minus e to the minus 0. And now we got to figure out what happens with this. Well, if you're not sure, you can always graph. If you don't know how to take the limits, so you can get an idea here. So clear, and I'll turn that plot off and come down, and I want to graph. I don't care about the negative in front, but I'll put it there. E to the negative x, and I want to see what happens. This is the limit process. What happens when b gets really large in this? So the x gets really large. So graph, zoom 6. Looks like it's headed towards 0. And I can go to the window and change it. Well, let's just trace. So let's just kind of trace. Follow it, and you can see it's minus 0.3, minus 0.1, 0.002, 0.001. And now it's going times 10 to the minus 4. It's getting really, really tiny. So this piece, as b gets large, goes towards 0. And a minus minus is plus, and e to the 0 is 1. So the answer to this is 1, and it converges. It has a limited size of area between this graph and the x-axis. Do this one by trig sub. Now you could easily say we need to put 3x, but the 9 is already squared. So we want to make a triangle where this is the positive, this is subtract, so this goes on the hypotenuse. 1 goes on the hypotenuse, and 9x has to go on one of these. I'm going to put it here. And so then the hypotenuse squared minus a leg squared is the other leg squared. So 1 squared minus that squared. That's the square of this leg, and so then I take the square root. If this is my angle, opposite over hypotenuse is the sine of my angle. And the opposite's 9x over 1. So if I want to know what to use for dx, I take the derivative here, and the derivative of sine is cosine theta d theta, and the derivative of 9x is 9 dx. So if I divide by 9, that's what I'm going to use for that. 1/9 cosine theta d theta. What am I going to use for this denominator? Well, adjacent over hypotenuse is the cosine of the angle. So that's the square root of 1 minus 9x quantity squared. And so this integral becomes the integral of dx is 1/9 cosine theta d theta, and this denominator becomes cosine theta, and the cosine thetas cancel, so, and the 1/9 pulls out, so I have the integral of 1/9 the integral of d theta, so that's like a 1 d theta. And the antiderivative of a 1 is 1x if it was x, but it's theta, so it's 1/9 theta plus c, but I don't want to leave theta. I got to go back to x's. So to solve for theta, I have to do the arc sine or sine inverse of this side, and so I got to do the sine inverse of this side, or arc sine. So this is 1/9 arc sine of 9x, or sine inverse of 9x, plus c. Now, you could go to the tables and get this answer, but I'm going to want to see your work on how to do this, how trig sub works. So I won't give you credit if you just tell me that's the answer. That's not what I need. I need you to show me that you know how to do a trig sub problem. Now, this has got definite limits on it, so you don't have to do anything more than just type it in the calculator. Let's do it on a newer calculator. So this is Math 9, the integral. This puts it in fancy. I should probably show you in both. Desmos will do this also. 0 pi divided by 2, and it's x sine of x squared dx. And it says it's 0.8660. If you wanted to know the exact value, that's the square root of 3 over 2, but it's 0.8668. It's really close to the square root of 3, I should say approximately. 86685. Now, I'll show you on the older calculators in case you're using them. To type this in here, it's Math still 9. The function is x sine of x, the whole thing squared, comma, I have to say that the variable is x. It's kind of what the dx does in some sort of way, comma, and we're going from 0, comma, and the comma is right there, comma, and 0 to pi divided by 2. close parenthesis, enter, and we get that 0.86685. 85, this probably should be rounded to 9 then. Anyway, that's the approximate. Just want to know if you can type those in on a calculator. Now we have, consider the area bounded by y equals the square root of x. The square root function looks like a sideways parabola. And y equals 2. 1, 1 goes to there. 2, 4 on a parabola. So bounded by y equals the square root of x, y equals 2, and x equals 0. So that has to be this. Spun around the x-axis. So this is going to go down to here and be here. So it's going to be kind of like a kind of thick at the bottom cup with a dip in it, because this is going to come all the way around. This is the part that's missing. We're looking at this that's not missing. Okay, so if we're just doing that, we're going to do, if I do the disk method, which is probably the one most of you would use, I'd do, it's got to be pi r squared for the large radius and minus pi r squared for the whole. Okay, oh, pi r squared h. So they both have pi. The h is the thickness of the slice, which is at dx. That slice happens here. There's the large radius and small radius. So now it's just a matter of the radius squared minus the radius squared. The large, since we're spinning around the axis, the large radius goes from the axis, the x-axis, to 2. It goes all the way up, and it's going to say, the outside is always going to stay 2. So large radius is 2 squared. The small radius is just to the curve, and up from the x-axis to the curve is y. So minus y squared. Oh, well, y squared is x. So I can replace the y squared with x, or the square root of x for the y, and square it, and that makes this x. So I'm going to have the integral, pi integral of 4 minus x dx, and x is going to go from 0 to 4, which is going to be pi. I could just type this in a calculator, but pretty simple integral to do. Integral of 4 is 4x, minus integral of x is x squared over 2, evaluated from 0 to 4. And so we get 16 minus 16 halves minus 8. 16 minus 8 is 8 pi. Now, if you were so inclined to do this one by shells, rings, it would be this spun around to here, making this tin can. So it'd be the integral of 2 pi r, and the radius would be just y. 2 pi r times the height of the can, which is x, because it's just out to the point. The point is over x up y over x. And the thickness of the can is dy, and we'd be doing dy from 0 to 2. And x is y squared. You square both sides, x is y squared. So we get 2 pi integral from 0 to 2 of y to the third dy, because x is y squared. And integrating that, we get 2 pi y to the fourth over 4, evaluated from 0 to 2. 2 to the fourth is 16, divided by 4 is 4, times 2 pi is 8 pi. So I did both methods. All right. Calculate the work done by a climber pulling a rope that is 2 pounds per foot and 150 foot long. The climber is piloting the rope on the ground beside her. The rope is dangling over a cliff. The climber has only a hold of the upper end to beginning, and her pack is tied to the bottom 150 feet below. The pack weighs 40 pounds. So everything is in weight already, so we don't have to multiply by gravity to get the weight density. So if they're going to lift the 40 pound up 150 feet, the work done for that, the weight is the weight force. The force is 40 pounds times 150 feet. So the work will be 15 times 4, 36,000, I believe. 40 times 4 times this would be 600 times 10, 6,000 foot-pounds. So that's the work just to lift the pack up. Now we got to lift the rope. And so if I have the cliff here, and it's 150 feet of rope at 2 pounds per foot. If I take a little chunk of this and figure out how much it takes to lift it, let's say I put X down here, Y here, which is what most of you would do, then this height is Y. That chunk needs to be lifted 150 feet minus Y. So the distance we're going to lift it is 150 minus Y. And the weight of that chunk, since this is linear density, 2 pounds per foot, I have to take it times how long that chunk is, which is dx. So that's the weight. That's the distance I'm lifting it. Oh, I guess this is dy. And I'm going to lift it, this chunk and all the chunks, over that 0 to 150 feet. So I have 2 dy times this. So I have the integral from 0 to 150. 2 times 150 is 300. This is not times the y, so I can't pull it out. And I have 2 times the minus y is minus 2y dy. And I can type that in my calculator. But the integral of 300 is 300y. The integral of negative 2y is negative y squared. evaluated from 0 to 150. So I put 150 in there times 300 minus 150 squared, and I get 500 foot-pounds of work to lift the rope, and the backpack is 6,000, so I add it to this, and we get a total work of 2,500 foot-pounds. Let's just check and make sure this works out. You guys like this calculator better or Desmos better? So on Math 9, 0, 150, 300 minus 2x, x, 2,500. Oops, sorry. Okay. Okay. Determine the work done pumping out of the top of a spherical water tank located 10 feet to a location 10 feet above the top of the tank. Of a spherical water tank, the top half of it. So we got this sphere, and we're emptying the top half to work done pumping out the top half of a spherical water tank to a location 10 feet above the top of the tank. Okay, so when we're doing these, we want to slice horizontally, and since it's a sphere, that will be a circular slice. And if you put your coordinate system, like most of you are liking to do, at the center of the sphere, then this place on the circle is x over y up, and to pump it out to the 10 feet above the top, and the tank has a radius of 8 feet, so this is 8 feet. So from the here to the where it's being pumped to is 10 plus 8, or 18 feet total. But this slice only has to go 18 minus the y. So we're lifting at 18 minus y. The thickness of the slice is dy, and the area, the volume of this slice is, actually the volume is pi r squared, so pi x squared dy, times the distance we lifted, and we got to integrate it from 0 to y. It's got to go there to the top of the tank, which is 8 feet. And we got to take this is the volume. This and this is the volume. So we have to take it times the density of water. And since this is all measured in feet, we're going to do 62.4. So I'm just going to type that into the calculator. Hopefully I'll do it someplace where you could see when I do it. 62.4 Math 9, 0 to 8 feet of pi r. R is x. Oh, but what am I going to put for x squared? Well, it's on a circle, And the equation for a circle is x squared plus y squared equals r squared. R is 8, so it's 64. So x squared is 64 minus y squared. Parenthesis. 64 minus y squared. I'm actually going to use y. Alpha y, just show you can do that. Squared. Close parenthesis. Times 18 minus alpha y. Whoop, I need to put that in parentheses too. Insert a parenthesis and insert a parenthesis. And the variable is y. And it says the amount of work is 1003701-ish foot-pounds. A thin rod linear density of this. So this is linear density. Find the total mass of meter long, then find the center of mass. So the total mass will be 0 to, how long was it? A meter long, and this is centimeters, so I have to go from 0 to 100 centimeters to make a meter of 1 over x squared plus 2. So that's the density, the mass density times the length. So that, since it's a linear density, this would be grams per centimeter times centimeters for the whole 100 centimeters. This will give me the total mass. And then to get the center mass, I do the same integral. Except doing torques on the top, so I have to multiply the numerator by x. So that makes it fairly easy to type in the calculator, especially if you type in the numerator first. Actually, let's do the denominator because I wanted the total mass. So math 9, 0 to 100, linear density is 1 divided by parenthesis x squared plus 2, close parenthesis, dx. There's the total mass. Total mass. 1.1 grams. Okay. Now, what's the center of mass? So this is a meter long. So the center mass, if we take a look, well, I don't need to look at it, but well, let's take a look at it. Oh, it's kind of like this one without the square root. Like 2 plus x squared. So get rid of this one. And if I go Windows 0 to 100, okay, that's going to do it. So it has some mass at the beginning, and then it drops very quickly. Window, let's make it go. Oh, ooh, I need the, I need the y to be small. Maybe 0 to 1. So a lot of mass here, and then virtually nothing. So the center mass is going to be really close to 0. let's figure out what it is. So it's the same integral. So if I go second enter, I bring it back, and I just got to put an x in here. Times x, I can just make the numerator x. And that would be the torque, and I have to divide it by my last answer. So divided by the answer I just had, and it says 3.8 centimeters. Remember, this is 100 centimeters long, so the center mass is at 3.8 centimeters from the, I guess, left end, since this is based on starting at x being 0 and going to 100. This would be the left end. Okay. And finally, the one you all love. F of minus 8 is 16. 4, 8, 12, 16. At minus 8, the area is positive. So this graph has got to go up, then the area is negative, and it's got to come down. And it's going to peak right about 2. So there's a max here. And the slope is 0 here, so there's a min here because it's going up here, probably coming down, but we don't know. So we're just going to say there's a min at minus 12, 14, 16, 18, 20. A min here. And it's going up from this all the way from here. It's got to be going up. Positive area. Got to be going up. And after that, still positive area, so it's still going up until here, where then we got negative area and it's coming down. So let's see if we can get this figured out. Now, the area tells you what's going on. So let's see. Each square is 1 high and 2 wide, so each square is 2. 2. Here looks like about 3.5. This one looks like 2, 4, 5. This column looks like 2, 4, 6.5. This column looks like 2, 4, 6, a little bit less, 7.5. And this column looks like 2, 4, 6, 8, 10-ish. Okay, so from negative 8, it's got to go up 6.5. So this is 8, 4, 8, 12, 16, 16, 20, 24, 28, 32. From 8, I got to go up 6.5. This is 4, 5, 6.5. I got to go up 5. Got to go up 3.5. I got to go up 2. I got to go up 1. I've reached my max. Boy, I put that arrow right on. That's surprising. That was total estimate. Then I got to go down 1. Then I got to go down 2, 2, 2. This is 1.5. And then 2, 2, 2, 2, 2. So I got to come down 1.5, down 2, down 2, down 2, down 2, down 2, down 2. And so it's straight line here. Okay, this is where you get messed up. So it says it's got to go up 7.5 and in there. So to go backwards, I got to go down 4, 8, 7.5. I got to go up 10. So I'm here. So 4, 8, 9, 10. I'd have to be here to be able to go up 10. Then I got to go 2, 4, 6, 8, 9. Or 10. That's close to 10 too. 9 or 10, so it's positive, so this has got to go up 10. 2, 4, 4 is 8, 10. So somewhere around here. And then 2, 4, 6 and a half, 6, and 6 and a half. I got to go up 6 and a half. That's 8, 6 and a half, something like that. This is about 4. So it's got to go up 4. And then it's got to go up a little, almost 2. And you can see that it's curving to have a minimum way down here. Count. Actually write in the numbers here if you need to keep track of how much up or down this curve has to go.